Hello there, my name is Isaac, and today I'd like to talk to you further about the unit tangent vector and the unit normal vector and why they are calculated the way they are. So I have two other videos on this that kind of provide a good level floor to build upon. What I'm looking at here is, why, if velocity is always tangent to the curve, then how come acceleration isn't always normal to the curve? Or perpendicular to the velocity. And we kind of talked about this last time, how acceleration has two components, the normal and the radial component. The tangent and the normal component. So normal component of acceleration points in, tangent component of acceleration points in the direction of motion. I just wanted to show here, if you'll remember, the unit normal vector is defined, so that would be n hat, is defined as the change in the unit tangent vector with respect to time divided by the magnitude of the change of the unit tangent vector with respect to time. And so we're pretty well aware at this point that this is just a normalizing component. That's just going to make our normal vector length 1. So the really important direction, the information of direction, is held within the dt, change of the unit tangent vector from here to there with respect to some time. And so what I've drawn up here is I've drawn two different velocity vectors. There are different lengths, which means that as we move forward in time, there's actually a deceleration in this direction. And so this velocity vector 1 is actually much larger than this velocity vector 2, which I have written as 1. Alright, so whereas with the unit tangent vector, it's always length 1 because we've normalized it. And so you'll notice that tangent vector 1 and tangent vector 2 are the same length. Well, if we line up the velocity 1 and the velocity 2 tail to tail, and we look at what is the change of velocity with respect to time, and we're pointing from this tip to that tip, and you'll notice that it's kind of backwards to our direction of motion, which indicates some deceleration. Whereas with the tangent vector 1, as we go from tangent vector 1 to tangent vector 2, they're the same length. And so what we end up with is this nice kind of centered arrow. So this blue arrow is actually pointing to the center of curvature. So it's pointing to the very center of the circle at that given point in curvature. And that's kind of cool. Whereas this one, you can tell, if we were to look here, let's look in between the two, and we were to take this change in tangent with respect to time and move it up here, you would notice that it's pointing definitely normal to the surface. Whereas if I took the dv dt, change in velocity with respect to time, and I moved it to this point on the radius of curvature, you'll notice that that is definitely not normal to this curve. And so that's why to find the unit normal vector, we take the change of the tangent with respect to time as our direction. So I hope this was helpful, and I'll see you next video to talk about radius of curvature.